Pau. Thank you for the invitation, giving a talk for the nth time about this topic. So I hope there are new people that never heard this talk before. Otherwise, I can just finish here. It's always the same thing. Okay, I speak up. So I will give you basically a sort of basic review of what we can do, what we expect to do about probing massive black hole binaries with gravitational wave observations of LISA and of pulsar timing. So since this is not LISA Astro-GR, but it's Astro-GR, right? And we can also probe these massive black hole binaries with pulsar timing, and there are a couple of talks, well, not many, but a couple during the week, so I will give a brief introduction also about pulsar timing for who doesn't know what it is. So this is the outline of the talk. First of all, I will give a small introduction about the formation and evolution of massive black hole binaries. So why we are interested in these sources and why we think we can do very nice things with gravitational wave observation. So the first amazing thing of this talk is that you see a plot with lines for the first time today, so which is already a big achievement. Thank you. So starting from the beginning, just a couple of words about our understanding of the evolution of structures and in particular of massive black holes in the universe. So the state of the art of our knowledge is that the formation of structures in the universe is hierarchical. Okay, so the galaxies we see today, they come from smaller building blocks that in the past basically merged together in a hierarchical fashion to form galaxies and clusters of galaxies we see today. What I plot here is basically the mass function of galactic halos, dark matter halos, okay, for different redshift, from redshift 20 here up to redshift 0, or down to redshift 0 if you prefer here. Okay, so what you see here is the hierarchical process. Okay, at high redshift, structures are basically small halos at most of 10 to the 9, 10 to the 10 solar masses, and that as time goes on, these halos basically accrete matter and merge with each other to form the massive halos that we see today that host spiral galaxies, elliptical galaxies, and clusters of galaxies. So this is just a visualization of what I just said. Within this dark matter halo, basically proto-galaxies form at high redshift. Okay? This is actually a visualization of a realization of a galaxy formation model from De Lucia et al. 2006. And as the time goes by, these small proto-galaxies merge with each other, forming the big galaxies that we see today. Okay? And this process is called hierarchical galaxy formation process. Moreover, what we see today in the universe is, in this galaxy, if we take a close look at the nucleus of these galaxies, is that in the center of these galaxies there are massive black holes. And one of the most interesting things that was a milestone in astrophysics in the last 10 years is the discovery of close correlations between these black holes and the properties of the Austin galaxy, in particular the property of the Austin bulge. So what I show here are these two relations. This is the M black hole, M bulge relation, and this is the M black hole sigma relation. Sigma is the velocity dispersion of the bulge, the galactic bulge. The mass of the black hole correlates closely with these two properties of the galaxy. This means, this is a clue that there was an intimate correlation in the evolution of this massive black hole with their host. Okay? So if galaxies basically form hierarchically, okay, featuring different accretion episodes and mergers. The massive black holes in their nuclei, they show this correlation with their galactic host. This points toward a hierarchical evolution of massive black holes as well. So what happened, basically? In these proto-galaxies that I show you here, okay, for some reason, there must be seed black holes, because the black holes we see today in galaxies are between 10 to the 6, 10 to the 7 to 10 to the 9 solar masses. And as far as we know, it's not possible to build a black hole from scratch of that mass, or it's very hard, or it's beyond our knowledge, let's say. So we need to seed some black hole, some smaller black hole in these proto-galaxies at high redshift. And how do you do that? So there are different mechanisms, basically. So what happens during the galaxy formation process in these protogalactic halos, the baryons basically start to cool down, okay? The baryons there are just hydrogen and molecular and atomic hydrogen, because there were no stars, we are in the early universe, basically, and there are no metals, okay? So in general, in this environment, the contraction and cooling process of hydrogen is very slow. And this means that a full clump or massive disk of gas can collapse altogether without fragmenting. Okay, so this is the basic idea. And depending on what is your main cooling mechanism, if you have efficient H2 cooling or efficient H cooling only, basically, you form this protogalactic massive disk and this protogalactic massive structure in different halos at different ratios. In particular, there are several scenarios that have been explored, and one is the POP3 scenario. Basically, when you have H2, efficient hydrogen cooling, you form these very massive stars, which can be up to several hundred solar masses. And the remnant, the natural remnant of the star at the end of the evolution is a black hole of a mass few hundred solar masses as well. That can be used as a seed black hole. If you have instead, if you don't have efficient H2 cooling, you have to rely on hydrogen only, and at that point, the cooling of hydrogen can happen only if the virial temperature of your halo is higher than 10 to the 4 Kelvin, so in much more massive halos, and the structure that you form is more massive as well. This way you can form, by direct collapse, seed black holes of 10 to the 5, typically, 10 to the 4, 10 to the 5 solar masses. Okay? And there is also another scenario where you can form a cluster of massive stars in this, if you have fragmentation in these protogalactic clouds, and also in that case you can form a seed black holes of 10 to the 3 or so solar masses. So there are several mechanisms to form the seed black holes. What happened then is that the seed black hole followed the evolution of the host galaxy. So when the galaxy merged together with another galaxy, if the other galaxy also hosts a black hole, there will be a formation of a massive black hole binary. The two black holes will sink to the center of the galactic remnant, and they will merge together and form a black hole which is more massive than the two black holes that we had in the beginning, also because accretion happens during this process. So this is the general picture, basically. Galaxies form by merging and accretion events, and the black holes in their center, they merge with each other and they accrete matter, powering the quasars that we see at high ratio, for example. Okay? And there are a lot, of course, of observational constraints that has to be satisfied for this model, and we have now several semi-analytical models based on analytical halo merger tree history or numerical simulation also of the halo of the evolution of the dark matter halos in the universe that can reproduce all these sort of constraints. So we think we have a fair understanding of how this black hole forms and evolves in the universe. I don't mean that we have a solid understanding. We have a fair understanding of this. Okay. But one of the important things in this scenario is that massive black hole mergers are predicted in this case, and actually several of them. And massive black hole mergers are the best sources of gravitational waves, and this is why we are interested in probing this thing through gravitational wave observation. So what I show you here is basically a gravitational wave spectrum from the inverse of the age of the universe up to kilohertz. In the top part of the plot, there are different gravitational wave sources. I don't know if you can read that, but I will explain you in a second. And on the bottom part, there are different windows that will be probed, or they're already probed, by different gravitational wave experiments. In particular, I want to focus on this range here. So this line from 10 to the minus 10 to 10 to the minus 2, 10 to the minus 3 hertz is more or less the frequency range which is spanned by a merging massive black hole binary. Okay? Merging massive black hole binary will lose gravitational wave, will lose energy because of gravitational wave, chirping, emitting waves at higher frequency during its chirp. And this is basically the frequency range discovered in this process. So you see on the bottom that there are two windows that are going to be probed, that are going to probe this frequency range. One is in the millihertz range, which is LISA or ELISA. I should cut down NASA. And in the millihertz range, at a much lower frequency, in the nanohertz, there is precision timing of millisecond pulses. So we have this family of events, and we have two windows to probe them. So let me go a little bit through these two windows. So you already heard a lot about the ELISA from Antoine, so I won't spend any word about defining the mission concept. What I want to show you here is just a typical, well, these are actually old plots from an old paper about LISA, but things don't change dramatically for these new designs. These are just distribution of observed event with LISA or ELISA, if you want, for different massive black hole formation scenarios that satisfy all the observational constraints and the theoretical understanding that we have. Okay? So you see there is a huge difference. So you can have models where you have, these are actually very, very pessimistic model where you can have down to 10 sources. And you can have a model where you have up to 1,000 sources in 3 or 4 years. Okay? And all of this is consistent with current observations. So we don't have now, at the moment, any mean to distinguish between these two models, these different models, whose difference is huge. Okay? And here what I show is the mass distribution of the detected event. So what I want to tell you in the next 10 minutes is try to answer this simple question. So now, we want to do astrophysics, right? Of course, we want to detect gravitational waves. We want to check the theory of relativity, prove relativity in the strong field regime. But we also want to use that information in an astrophysical useful way. So the question that we are asking now is, so given a set of gravitational wave observation, what is the astrophysical information about the underlying massive black hole population that we can extract? So given a set of observation, can we infer something useful about the parent population of massive black holes? Can we put further constraints on the massive black hole formation and evolution history? Can we, for example, distinguish between low and high massive models, for example, or distinguish between different accretion modes of the black holes? So this is a work that we started with Jonathan, Emmanuel, and Marta a couple of years ago. And we did it for LISA at the time, and then we transported basically all the tools that we developed for this new ELISA study. And I will show you some results here. So first of all, what we did, we took as a simple basic concept, a proof of concept basically, we took 4 massive black hole formation models different for 2 physical things. One is the seeding mechanism, so we took small versus large seeds, and the other is the accretion geometry. We took efficient accretion versus chaotic accretion. Okay. So a word about this. So this is what is the point here? The point is that how the geometry of the accretion of the black holes has important consequences for the properties of the black hole itself. So we know that prograde coherent accretions spins up the black holes. Okay. So in this case, you expect a very different spin distribution, a spin distribution which is biased toward high spins. Whereas chaotic accretion, where you have lumps of matter accreting in all directions with respect to the black hole spin, will tend to spin the black hole down. So the spin distribution of these two populations of black holes will be very different depending on the accretion mechanism. But this also has an important consequence for the mass accumulation, because the higher is the spin, okay, the higher is the efficiency conversion of matter into radiation during the accretion process, and the lower and the slower is the mass accumulation into the black hole. So also the black hole mass function depends on this thing. So I want to point this out because in this exploratory study, we didn't consider spins. We just considered mass and redshift distribution. But we will see, nonetheless, that you can distinguish between the two models only by means of the mass distribution. So we took 4 different models where we mix small seeds with efficient accretion, small seed counting accretion, and the same for the large spins. And we construct basically this, and we follow the evolution of the massive black holes during the cosmic history. And then what we did, we said, okay, suppose now that we observe a set of massive black hole binaries with our detector. So can we recover what was the parent distribution? So how we did it is, I go to the step by step into it. It's quite simple. So basically, what we did was to construct a detector transfer function. So given your detector, first of all, I must say we consider 3 things: mass ratio, and redshift of the binary. So we have a 3-variate distribution of mass ratio, and redshift. Okay. And in this 3-dimensional space, we build the detector transfer function, which is basically, depending on mass ratio, and redshift, what is the chance that your detector will detect that system, okay? Which is not 0 and 1. It can be any number between 0 and 1, depending on the inclination and the orientation of the system in the sky, okay? So you build basically this transfer function. Red means transfer function equal 1, so all the binaries with this mass that you can't read, but it's between 10 to the 5 and 10 to the 7. And this mass ratio at this redshift, which is 0.5 here, can be seen, okay, by your detector. And of course, if you go at higher redshift, you lose the low mass ratio and low mass binaries, but you can still see equal mass and very massive binaries. So you build this transfer function. Then you apply this transfer function to your intrinsic distribution, which is the theoretical distribution predicted by your model. So what you obtain is what we call the theoretical observable distribution, okay? Which are for each model, these are the distribution that has to be compared to what you actually observe. Then what we did was to draw a Monte Carlo realization of any of these models, okay? This is actually one of the Monte Carlo, these are distribution of mass ratio, and redshift in a Monte Carlo realization of one of these specific models. And then compare what we get from the Monte Carlo realization to this theoretical distribution and see if we can assign to a realization of one of the distribution the correct parent distribution. In all of this process, we also consider detector errors. So we assume that each event will be detected with some signal-to-noise ratio, and we put error bars in the mass, in the redshift, and in the mass ratio that we obtain. So the exercise is, in a sense, complete. There are also errors in the determination of the parameters are included. So what we did then, given a set of observed data with errors, we compute the likelihood of having that set of observation for a given parent model. And then we compute the odd ratio between the likelihood, the odd ratio of the likelihood of the data coming from model A to the data coming from model B, okay? To compare two different models. And we can also assign a confidence, which is the probability of model A, which is the probability of the data, the likelihood of the data given model A over the normalized to the likelihood of the data given model A plus the likelihood of the data given model B, and build probability cumulative distribution function over thousands of Monte Carlo realization. Why I'm saying all this is because I want to show you then how we present the results. So once we have this, we do thousands of Monte Carlo realization of each of the model, and then contrast the observed distribution with all the parent models. And to see if you can compare, if you can find what is the parent distribution. So there are two ways of giving this information. One is through the receiver operator curve, where basically you have a model A, which is let's say is the true model, and a model B, which is the false model. You select a threshold in your odd ratio here, okay? And then the detection rate is the probability that the realization of the model A actually exceeds that threshold. And the false alarm probability is the realization of the model B, which is actually the false one. It's over it exceeds the selected threshold, and which is what you call false positive. Of course, if you can distinguish perfectly between the two models, so this curve would be something like this, okay? So you never have false alarm probability. So you are always able to say, okay, this realization came from model A. Okay, I never have false alarm probability, which is always 0. But of course, it's never like that, because you have uncertainties, you have a finite number of events, usually 20, 30, 40. And this is a way to represent the results. So the more this curve is close to this angle here, the better is the distinction between the models. Okay? But then there is also another way to reproduce to show the results, which is a bit more complicated, but it closes all the information. Because here, if I show you a plot like this, you don't know what is the odd ratio that I choose. Okay, so we don't know if this ratio, the ratio that I defined for distinguishability was a likely ratio of 100 or of 1.1. Okay, so in some sense, the information is incomplete here. So what we did was to build this cumulative distribution function of confidence, which are these other plot on the right. So what is basically shown here is the cumulative distribution confidence of model A, which is the true one in the upper curve, and the cumulative distribution confidence of model B, which is the low one, which is the false one. So how do you interpret this curve is in the following way. So select, this is not a particularly nice example, but select a confidence, you set the confidence threshold for which, okay, I want a confidence of 0.95%. So I'm here, okay? So this upper curve tells you what is the percentage of your realization, of your 1,000 realization, which exceeds that confidence level. So in this case, it's less than 10%. Okay, the two models are difficult to distinguish at that confidence level. The lower curve basically tells you what is the fraction of the realization of the false models that you cannot rule out at that confidence level. So in this sense, they give you a complete information of what of your two models. So it tells you if your two models are really distinguishable as a function of the confidence level that you want. So you have a more complete information. But the two things are equivalent. So we did this exercise for these catalogs in the ELISA study context. And here I can show you the results. So these are configuration C2, which is the current preferred baseline, and this is configuration C1, which is slightly worse, which has a slightly worse noise at low frequency. So here I show you the receiver operator curves, and here I show you the cumulative distribution function. So that the information in these two curves, let's say, is equivalent. Okay. So what you see here is that and the 6 curves are comparison between different pairs of models. So what you see here is that basically any model is very well distinguishable. Okay. So you know for sure that, almost for sure, that one realization was drawn from high massive model with coherent accretion or low massive model with chaotic accretion or so on. Okay? And the things, of course, are slightly better for configuration 2 with respect to configuration 1. The same information you see here. So if you choose a confidence level of 0.9, 0.95, you see that in almost all the models you have 95% probability or so to pick the correct model. So in this sense, ELISA, okay, in each of these configurations is a fantastic instrument to do astronomy, because it's a fantastic instrument to pick basically these differences in the population models. This is, of course, just an exploratory study, and we did several other things. For example, here we just compared very well-defined different models. So the universe is either A or B. Of course, we won't have any of that knowledge, of course, by the time this mission flies. We will have a range of models. So we also did some exploratory study in which we mixed two of these models and we looked for the mixing parameter with the same technique. And also in that case, you can guess that, for example, model A or B were mixed, and to what level. Okay, but I won't show any result here. So this is just to say what we can do with this mission. And I want also to stress that all of this goes down with very simple 2pn circular waveform, so no information about merging and ring down spins. If you include spins, actually here you can do way better. For example, this curve here, which is not perfectly, which means that these two models are not perfectly distinguishable. For example, if you require a 0.9 confidence level, you just have it in 70% of the cases. Yes?
Real quick question. I would expect that with that model, you probably didn't have very much constraint on the redshift. So my guess would be that this was basically coming from the mass differences.
Yes. Most of the information comes from the mass distribution. That's true. So I was saying that, for example, these two models, which are not very well distinguishable, are the small seed coherent and chaotic accretion. So since we don't use spins, we have a hard time to distinguish between those two. But we have some new results now, which shows that also if you include the spins, actually we just include the spin of the remnant in that study. You can distinguish much better between these two. So once you have full waveform and you consider spins, whatever, you will do actually a much better job than this. And of course, now we are working on more sophisticated model in which we have parametric models for the black hole population to see how well we can pick the interesting parameters, which can be, I don't know, the mass function of the initial seed or the mean accretion efficiencies of the black hole, if we can constrain those parameters with this kind of observation. But that's much more, tricky, so we need more time to do this.
How many actual detections would you have to have in order to have the significant statistics?
Actually, it depends. In this case, it really depends on the two models you pick. For example, if you pick one, I don't know, high mass seed coherent accretion versus low mass seed chaotic accretion, with 6-7 detections, you have almost perfect distinguishability between the two. Yeah, but in the case, for example, in this case where only the spins are different, since we don't use the spins here, still with 50 or so sources, you have these difficulties in distinguishing the two.
So basically, you're saying that regardless of the uncertainties about how efficient the instrument will be, etc., it's almost certain that you will be able to distribute it.
Well, regardless.
These are very small numbers.
It depends on of course, on your instrument. For the configuration C2, you do better with respect to configuration C1. But with all the configuration we consider, you keep the ability of doing this. It's not that we do this the scoping study and we lose all the capability of doing astrophysics with gravitational wave observations. So it's still a very good target for a very good goal for this mission. Okay, Pau, who is the chair? How much do I have?
You have 13 minutes. 13.
13 minutes. Okay, 13 minutes to go through the other window here, which is nanohertz frequency, and the tech is timing of millisecond pulsars. Okay, so just to tell you how it works. So pulsars are basically the best clock we have in nature, and pulsars. We detect their pulses, and the radio pulses come to Earth, and we detect them with our gigantic radio telescopes. And of course, what you do in pulsar timing is actually the following. So you have your series of time of arrival, and you fit a model into it. And what you're left, the model basically is for your pulsar, the position in the sky, the period derivative, first and second derivative of your pulsars, whatever it is. And then you're left with the residual. Okay? Your model fits your data, and you're left with the residual in your time of arrival. If your model were perfect, and if you had no noise in the data, then this residual would be 0. But of course, your model is not perfect, and you have a lot of noises in your detection, you have a lot of effects that you can't take into account for properly. For example, the dispersion in the interstellar medium. Okay, you can subtract it, you can take into account for it, but it depends on the distribution of the interstellar medium between you and the pulsar, so it's not that easy to do. And of course, what you can have is a gravitational wave. And if there is a gravitational wave passing through between you and the pulsar, and you didn't take into account for it in your model, then it will show up in your residuals. You have a sinusoid, you don't fit for it. You fit out your model, and you see a residual with a sinusoid. This is the basic idea, okay? And in fact, what happens is that the gravitational wave will cause a modulation in the millisecond pulsar frequency, and if you integrate this thing, you will get this quantity, which is the timing residual, okay? Just to give you an idea of the order of magnitude, the timing residual, since it's an integral of the amplitude, okay? So the integral of an amplitude, it takes out 2 pi f. So the residual is actually an amplitude, because your amplitude is a sinusoidal wave. Okay? So your residual is basically your amplitude divided by 2 pi f. And for typical masses and distances, the numbers that you get are something like this. So for a 10 to the 9 chirp mass binary at 100 megaparsec, this number is of order 30 nanoseconds. 30 nanoseconds is very small. So we're talking about really precise timing of these pulses. Just to give you a reference now, within the different collaborations that are studying these pulsar timing, that are timing these pulsars, there are few pulsars which are now timed better than 100 nanoseconds, around 50 nanoseconds, okay, on a couple of year time scale. And many of them are between 100 and few hundred nanoseconds, and many more are timed with a residual of order of microsecond. But we are not far from the accuracy that you need to see this kind of sources, this kind of signals. Just to give you an idea, okay. So, how do you model this signal? Of course, you don't have just a massive black hole binary at 100 megaparsec, but you will have a population of massive black hole binaries. So again, we need a model for describing this population. And what we did was to take the Millennium Run, which gives you distribution of, which gives you the merging history of massive galaxies on a large volume. So you have a lot of statistics for massive things at low redshift, which is what we are interested in here. What we are interested in here. Then we populate these merging galaxies with massive black holes according to some of the black hole galaxy relation that I told you before. And we construct the distribution of emitting binaries at any redshift time, at any redshift and mass and frequency, okay? We adapt all this contribution, and what you get is something like this, for example. So what I put in here, so these are signals from individual massive black hole binaries, and these are timing residuals in nanoseconds, and these are the cumulative timing residual. And this is for 5 different pulsars. So the signal you're looking for is nothing like a nice sinusoid or anything. It's basically a red noise with some periodic features which are probably due to some particularly bright nearby source. Okay, and what people have to deal with is these kind of signals buried in the noise into 50 or 100 pulsars and try to correlate the data to get the signal out. So it's not an easy task. If you take a power spectrum of this, and actually what I plot here is the amplitude against the frequency, whereas here is the timing residual. The difference between the two is the frequency. The timing residual is the amplitude divided by a frequency.
Where does this very long time scale come from? The year time scale? It's from individual sources, or it's the? So let's suppose that I time a pulsar for 5 years, and I collect data. This is the evolution of the timing residual within the 5 years.
So if I take the power spectrum of the signal, I get something like this. So here you see how the signals add up, basically. I show only sources up with the residual larger than 0.3 nanoseconds for clarity. But you see each green point is an individual source, and the blue thing is the total signal. Okay? All the individual sources will add up together to give this level of signal here. Okay? So what you have is actually something which is very similar to, partially similar to the whiteboard binary problem for Lisa. So you have a population of sources which can be considered stationary to some level. And they add up together in a sort of confusion noise on top of which you may be able to resolve some individual source. Then, okay, this is just to show that this signal, this is the level expected with uncertainties, is well within the reach of probably current post-rock timing campaign, and is very well in the reach of the planned SKA. So at some point, these post-rock timing people, unless there is something very wrong in what we predict here, or something very wrong in the detection technique that we use, they will see this signal, okay? And I have no doubt about that. So you can write it down. The statistics of individual sources, here you see the number of individually resolvable sources as a function of timing residual. So you see, if you go down to a nanosecond precision, you will have at least a dozen of individually resolved sources. And these are very nice because they give you possibility to do some multi-messenger astronomy, which is the topic of my last 5 minutes. So I want to point out, so why I'm talking about multi-messenger astronomy, that these sources are very massive. So this is the Chirp mass distribution. This is 10 to the 8, this is 10 to the 9. So these are massive. So these are very massive binaries. And they are cosmologically nearby. This is redshift 0.1, this is redshift 1. Okay? So you have a population of 10 to the 8, 10 to the 9 massive black hole binaries in spiraling at redshift less than 1. If these sources are accreting, if they emit something, you will see them, okay, because they are massive, they are close. If they are also bright, okay, there is a very good chance that you will be able to pin down the emission of these systems. Of course, one issue is to localize them in the sky, and I think Neil will talk about this. But so if you will be able to localize some of these individual sources with few degrees precision in the sky, there is a very good chance to find a counterpart if there is one. So, want to show you some result that we did about this counterpart, this multi-messenger astronomy possibility. So we consider a massive black hole binary merging, spiraling into a circumbinary disk. So here the situation is the binary is at subparsec separation, and the torques of the binary excavated the gap in the disk. So you have a circumbinary disk, you have the two black holes within the circumbinary disk, and there are streams entering this low density region which are accreted into the black hole. So we set up a simulation with an SPH code gadget, and we let the system evolve, and we studied the accretion properties of the source. This is the accretion curve that you get, and you see that it's highly periodic. And this is very nice because if this curve is highly periodic, then you can look for periodic sources in your all-sky surface. And one very interesting thing, which I want to explain, is that the variability is related to the streaming material and to the accretion on these mini disks. It's not related to the circumbinary disk. The circumbinary disk is very stable. And if you look at the spectrum, if you just look at a very simple spectrum of the source, it's something like this. Here you have the emission from the circumbinary disk, and here you have the emission from the two mini disks. Okay? So this circumbinary disk thing will be very stable. And the two mini disks the emission of the two mini disks will vary a lot. So we will have probably a sort of switch on-off kind of accretion situation. So it's probably hard to get these sources in the optical, but it will be much easier to get them in the X UV band. So for example, and I conclude with this, in 2012, there will be, or 13, eRosita will be launched, which is an all-sky X-ray monitor, which is supposed to cover the sky 10 times in 5 years to a fantastic flux limit, which is 3 × 10⁻⁴ error per second centimeter square. And if you do a plot which is very famous among X-ray astronomers, which is the log-n/log-s distribution of sources, you see that these are the number of sources per square degree as a function of the flux. You see that with eRosita, you may be able to detect up to 0.01001 per square degree, means few hundred in the whole sky, up to few hundred of these periodically variable sources. And this is probably a very nice prospect to look for these things. I guess I'm running out of time, so I will skip the iron line part, but you are very welcome to look for it in our paper, Sesana et al. 2011. So just to wrap up, I just leave here my conclusion, and I'm pretty sure that so this ELISA, if we go through, will be a fantastic thing for not only for fundamental physics but also for astrophysics, because you can get information about the early history of this massive black hole that there's no way you will get any, with anything else, even JWST, forget it. Okay, so this is actually very important. And also the prospect of detecting massive black hole binaries with closer timing are good, and we look forward for it in the next decade. Thank you.